Hey guys, welcome back to Genius Learning. All right, so continuing on with exam reviews, we got this scenario. We got a building 15 meters tall and somebody's throwing a ball or something, right, in a parabolic shape all the way to it lands on the floor. Okay, the angle that he's throwing it at is 33 degrees above the horizontal, and it's launched with initial velocity of 30 meters per second. The height from the horizontal angle that it was launched at is denoted here, and then it goes all the way down to the ground, right? And then this is the displacement in the x direction. All right, so remember that a lot of these problems are not going to be drawn out for you, and so things like this are not going to be drawn out. The horizontal line is just going to be said, and so try to imagine it while you're doing the problem, and the more problems you do, the more you can see how it could probably look. Okay, so first question. Okay, we have, what is the maximum height above the roof that the rock reaches? Okay, so the maximum height above the roof, this is the roof, okay, and so we want to know this from here all the way till here, the max height. Okay, when you hear max height, you should already think alarm systems and things are going off and you don't know why, and then you realize V final in the Y is equal to 0, right? Because if you throw something up, right, it stops all the way at the top, turns around, and comes back down. So the final velocity in the Y direction is equal to 0. Remember that if you throw something in a parabolic shape all the way at the top, only the Y direction is equal to 0, right? Because the Vx direction is still moving. That's why it's still traveling in that direction. Oops. All right, so now we have this, right? And let's write an equation that's relevant to knowing this right here. Okay, so we want to know the height above the roof. Okay, so technically we want to know the change in y, right? That also can be written as the height. So these two things are the same, right? That's what we're looking for. This h, or you can write it as delta y. So that's what we're looking for, okay? This is what we know when we're dealing with max height. And so knowing that, let's write an equation that has things like this in it. Okay, so we got velocity final, y, is equal to velocity initial, y, minus gt. Okay? It's an equation relative to this information, and it's useful because we don't know time. We don't know the time it takes to get here or here. Velocity initial in the y, we do not know, but we do have an angle, so we can open this up, and this is 0. So let's just plug things in, okay? We got this being 0, okay, so that, and let's change this to V initial sine theta, right? So it's undercover form, and then minus gt. Okay, so we have this now, and let's solve for t. So we got t is going to equal V initial sine theta over gravity. Okay, we know all these values because we got V initial, we got the theta, and we got gravity. So we're going to put t is equal, let me just put this here, we got t is equal to 30, we got sine of 33, and we got 9.8 on the bottom. Okay, so finally we're going to get t is equal to 1.66 seconds. Now stop right here and think, what time did we just calculate? Okay, we just calculated if the max height is equal to 0, right? This time corresponds to a maximum time or maximum height time. And it's the time that it takes for the rock to go from here to here because it's above the roof. So this is what we just calculated. So I'm just gonna write a little subscript here, maybe M for max height, okay? Now that we have that, right, what was our initial question? Let's look for how high above the roof it goes, like the max. So we found time. Let's write down this equation here to see if we see anything relative that we can use. All right, so we got delta y is equal to velocity initial y times time minus 1/2 g t squared. Okay, so this is the formula. And let's see what we know, we don't know. So let's see, I always get this part. We know this, but in its undercover form, right? So let's write V initial sine theta, okay? Times time minus 1/2 g t squared, delta y. You see, because looking at this, I'm like, whoa, what, I don't have those things. But if I write it like this in its vector, form, or its component form, then I see immediately V initial we have, right? And sine of theta we have the time it takes to get there, because that's the max height time we found here. Gravity we know, time, so we have everything we need to calculate delta y, which is our height. So perfect, smooth. Let's put all the values in. We got 30, we got sine of 33, the time we got was 1.66 minus 1/2, gravity is 9.8, and again the time is 1.66 squared. All right, so plugging that in the calculator, and we get delta y is equal to 13.5 meters. Okay, so this is also the max height above the roof. The max height, or H, okay, above the roof. This is what we just calculated here, 13.5 meters. All right, so let's do this, make it feel important. Okay, perfect. Now let's move on. B. Okay, we got, what is the speed of the rock just before it hits the ground? Okay, so now we're talking about, let's see if we can highlight that area so we know clearly what's going on there. Okay, so it says the speed of the rock just before it hits the ground. So just before it hits the ground, right, we want to know the speed of the rock, meaning this velocity here, velocity final. Okay, so now let's see how to go about this. You're gonna need, okay, so when you write this, right, you should think already that is not in component form. Shame on them, and you should definitely write in component form right now before anything else, because our goal is to get V final. All right, so the magnitude of the velocity final is what we're being asked of. Okay, so the speed of the rock just before it hits the ground, that is not specifying the X or the Y, it's just the middle, the diagonal one, meaning like the magnitude. So that's what we're aiming for to answer this question. Inside of this, we need to know that we're gonna need to find V final of X, right? And we're gonna need to find V final of Y. Okay, so we know what these things are. So just like here, V initial Y was this, V final Y and V final X is the same thing. So we got V initial cosine theta, and here V initial sine theta minus GT. Okay, so this equation here corresponds to this one, right? And the same for this one, except it doesn't have a gravity term. So you guys should be familiar with these two equations. But I'm writing them down now because knowing that we have to find this means discretely that we have to find these. Because I'm going to show you the next equation that uses both of these to find this. So these are just deductions I'm making before I even start. Okay, to find this, right? Let's put it in a different color. Okay, so to find this, I'm gonna need the square root of velocity final x squared plus, excuse me, velocity final y squared. This is the equation that I'm gonna need to find velocity final, or I'm gonna need to find the speed just before it hits the ground. This is what they're asking for. This has these two things in it. That's why I wrote them here and here. So I'm just kind of like working backwards. I know what I want. I know the equation to get it. The equation has these two things in it. So I'm gonna write the equations for that to see what, you know, I'm missing or what I have and play with it. All right, so that's it. So now I put everything out there, and let's look at both of these. V initial we have, okay, cosine of theta. We can use, so we have this, we have the velocity final x, right? But we don't have the time that it takes for the rock to go from here all the way down here. This time right here only corresponds to the height. So we don't have the time. So let's find the time. We need to get another equation now in order to find time, because that's the missing factor here. This one's good to go. Here we got a problem. So now let's look at another equation that we can use. All these equations. So I'm gonna use delta y. Okay. This one right here, okay, is exactly what I'm gonna write down, but I'm gonna write down in its expanded form. So I'm gonna write y2 minus y1 is equal to velocity initial sine theta times time minus 1/2 gt squared. You may be thinking, why did you pick this formula? I don't know. I could have also wrote the displacement for the x, right? But I'm going with this one first, right? And the displacement in the x is going to give me the same problem where I don't have t. So I know that at least with this one, from previous problems, I get ugly things like quadratic, and I'm able to solve for t. When I don't have the t for the displacement in the x, I'm kind of stuck. So this equation here, let's see what we have. Right, we got y initial and y final. These two things, don't let them confuse you. So we're gonna go through that first. And let's see, we got y initial is where the rock started. And the rock started here. So initial is 15. So right under here, I'm gonna write -15. Y final, it ended up all the way right before it hits the ground. So we're just gonna say 0. Okay, and then we know V initial. So we're gonna write 30, that was given. Sine of 33. Okay, and then we don't know the time, minus 1/2 9.8 t squared. Okay, so now from doing a couple problems that have quadratic and hating it so much, you should definitely see what we have here. Nasty quadratic. not that nasty. So let's just write it out, make it equal to 0. I usually like to make the t squared term positive. So I'm gonna put this on the other side of the equation, put this on the other side of the equation, leave that there, and then the right side will be 0. Okay, so what am I doing using this? I'll use this color. So I'm gonna do little brujeria algebra. Not really, I'm just gonna rearrange things and see what happens. So I got that, and minus 15 equals 0. Okay, perfect. I like to have it like that. You may like another way. You always need to make it equal to 0 though. And I like to identify what my A and then what my B is, and here is C. Just so there's no confusion. All right, now let's write it out for anyone that has not memorized the quadratic, or rearranged it in a way that you don't feel comfortable. Okay, so let's do t is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so plug in the values into here. Remember that this is negative 4 and AC. One of these is going to be negative, making this term positive. Always. You're never going to have a negative under the root. We're not doing imaginary numbers. So if you have one, or if you have a negative under the root, you're doing something wrong, and check the sign for these things. Okay, so plugging it in, which is the fun part, I will definitely leave to you. You will get t is equal to 4.09. See, or you can just trust my word and my calculator. Don't. Check it yourself and go through the motions of calculating it. So this is the time it takes for it to go all the way to right before it hits the floor. So right over here. All right, perfect. That's what we were missing here, right? And now we have it. So let's plug it in. All right, I'm gonna write this one and this one together, because those are the two things I need in order to answer this. Okay, so let's all right. So I'm gonna do this first. So V initial, so I'm gonna put, now that we found the time, V final X is going to be 30 times cosine of 33. And so V final X is going to be 25.16. That's in meters per second. We found one of them that we need. Okay. Now let's put this one here with the t value, the time value that we got for the whole time of the path. Boom, boom. So now we got V final Y is equal to 30 sine of 33 minus 9.8, and the time now is 4.09. Okay, put that in the calculator, and negative 23.74 meters per second. All right, negative because, if you're looking at this as the magnitude, meaning like the direction it's coming in at, this is velocity in the x, this is velocity in the y, and you can see that it's facing down. So don't be alarmed if you see that negative there. Okay, and like usual, I'm running out of space. And so I'm gonna write on a piece of paper. We have these two things. Let's see how much space. Okay, so we have these two things here. Now let's continue. I'm guessing here. Yeah, right above. So B is what we're doing here. We got these two. We just found this. Okay. And so now let's find velocity or the speed right before it hits. So V final magnitude is gonna equal, let's go with X, V final and the X first. So that's 25.16 squared plus negative 23.74 squared. Okay, put that in the calculator and you should get V final right before it hits the ground is going to be 34.5 meters per second. Okay, and looking at the what we have, it makes sense because you're throwing it from a rooftop, right? And so it's gonna leave at 30, right? And it still has time to gain speed, those 15 meters up that you launched it at. So from here to here, it could gain, you know, about 4 meters per second or whatever. You know, it makes sense that it would be a little bit over 30 since you're throwing it on top of a building. Okay, so last question. So C, what is the horizontal range from the base of the building, right, where the rock strikes the ground? So basically, what is our change in X, or our displacement in the X? So the range, right, the term range and displacement in the X are interchanged sometimes, but the difference is that range only and specifically explains from the initial point all the way till the object reaches the ground again. Okay, so in a perfect scenario, it would be, let's say we launch from the ground. Okay, now when it hits the ground again, this is your range because it describes the maximum distance it went in the X. Delta X, let's say you have like a delta X that you want to find that's right there. That is how you describe the delta X, I mean the displacement. All right, anywhere inside of the maximum. The displacement can also be the whole thing, coincidentally, but range is only specific for the maximum. Okay, so just in case you're confused about that. And if you weren't, whatever. Now, obviously, we're just going to need an equation that has the delta X, you know, some type of range in the X direction. So we're going to use, let's see if it's already here. Whatever, we'll write it in. We got delta X, right? Displacement in the X is going to equal V initial cosine theta times time. Okay, you should be familiar with this equation. We have the total time that we need. We have the theta and we have the initial velocity. So we got 30 cosine of 33, and the time we're going to use is 4.09 seconds, which is the entire length. All right, so plugging that in, now delta X is equal to 102.6 meters. Okay, or you can write range is equal to 102.6 meters. Okay, and we can do that because now at the maximum time, right, it's all the way at the end, so it's appropriate either one. Okay, so a little bit more practice on the quadratic, right? Definitely understanding how to solve one equation to make another equation. You know, seeing what you're missing from the beginning is really crucial. I like to write out what it is that we need and the things that we're gonna need to get there. Stuff like that. You know, you can, you know, just be smart and know all your stuff, or be like me and I write down a lot of crap. So, hope that was helpful. Thank you guys.